So it's my great pleasure to introduce our speaker for this Research Day's keynote lecture, and at the same time the inauguration lecture of Professor of Music Research Tuire Kuusi. I'll say a few words more. Tuire started her professional career at the Sibelius Academy a while ago in the late 80s, and she's had a number of different positions, from assistant to part-time teacher to lecturer to department head and so on. I'm sure I'll forget some of them. The list is long. In 2015 she was appointed Vice Dean of Doctoral Education and Research, and has since divided her time between duties of being both a Vice Dean and a Senior Lecturer. She is a very skilled musician, holding a piano diploma from the Sibelius Academy, and has extensive experience in teaching music theory and ear training on various levels. I think you could say that Kuusi is one of the leading experts in the perceptual psychology of music theory, particularly in the field of non-tonal harmony. Her works have been published in such internationally recognized peer-reviewed journals as Psychology of Music, Music Perception, and Journal of New Music Research. Her research sheds light on how musical concepts and characteristics affect perception of similarity and the listener's ways of processing harmony in music and the relation between harmony and emotions. She has also cooperated in research projects studying creativity and musicians' health. Tuire has also been successful in receiving research funding, and her work has been described as path-breaking in its significance, of great originality and imagination, and rigorous in its conduct. I think those of us who have had the pleasure of working together with Tuire are especially happy to welcome you as a professor. You are very experienced colleague, and also a respected one, well liked. You were chosen Teacher of the Year in 2011 by the Union for University Teachers and Researchers in Finland. We know that you are always well prepared, extremely committed not only to your own work, but to the research community, to the Sibelius Academy, and to promoting the role that music can play in our society. So it's great fun to continue to work with you, Tuire, and let's give a warm welcome to our new Professor of Music Research and our Vice Dean, Tuire Kuusi.
Thank you all. I'm very happy to be here today, and it was very nice that you asked me to give this inaugural lecture just today and within the research days. When I started to think about the content of this lecture, I checked the theme of the SibA Research Days first. It was how to tell about your research and how to give a research talk. Then I checked what is an inaugural lecture. Usually it's about one's own research described in a popular way. So how to combine these two? In my opinion, a good research talk is not too long, and it shouldn't concentrate on too many points. But I was asked to talk for about an hour, which is not short. And so I decided that I create some kind of a narration about some issues during my career. And I will talk about research as a continuous process, where one idea leads to another, and one result leads to new questions. I will talk about research as a process, where curiosity leads, and where attempts to solve one problem might lead to a complex snarl of new problems, and where persistence is needed. At the same time, research is a process where good luck and good advice from other researchers is worth its weight in gold. I will concentrate only on one branch of my research, namely research on harmony. I started my research with the concept of similarity. I had learned about mathematical similarity models that were used in pitch class set theory. They were used to calculate similarity between two set classes. And I was interested to see if the results correspond with empirical similarity between harmonies. That is, how people estimate similarity between chords. Sounds simple. The mathematical similarity was actually the easy part. All these similarity models had one and only one formula by which similarity between set classes was calculated. This formula is the cosine. Even though it might look a bit difficult, it's actually not. In this formula, the similarity between set classes is calculated as the cosine of the angle between the interval class vectors of the set classes. And as the angle between the vectors decreases, the cosine of the angle grows, indicating increasing similarity. I promise this is all mathematics today. So the mathematical models gave unanimous results for abstract similarity between set classes. But with similarity estimations, we face a problem. The abstract set classes cannot be perceived. Instead, they must be represented by musical items. And since I was interested in harmony, the representatives were chords. And when I started to work with the representatives, I soon understood that the representatives have many characteristics that are not related to the concept very closely. To some extent, yes, but not all. And yet, those characteristics affect similarity estimations. So very soon I noticed that my simple research problem had become a set of new complex research questions, and that there was practically no earlier research on the issue, indicating that the literature did not help me when I tried to solve the problems concerning how to compose the representatives. Earlier research on similarity between chords showed that chordal characteristics are a strong factor in similarity estimations. Unfortunately, the set classes were mentioned seldom, if at all. By affecting the chordal characteristics, I was able to affect the perceived similarity. But what about the set class properties? How to make them affect similarity? Which competing characteristics should I use when I was composing the test items? Now I will use some figures to demonstrate the main problem. Let's take a concept. Let's take a lion as a concept. The concept of a lion cannot be seen. You each can imagine a lion. It's a representative of the concept. And if we started to talk about your representative lions, we would probably notice that they all are different to some extent. Yet we think that a lion is more similar to another lion than to a rhino, for example. I chose this drawing as a representative. And if I now ask how similar these two lions are, you would perhaps rate them very similar, but not identical. But if I show you other pictures of lions, we would get different results. All these are lions. The concept is clear, but what about the similarity between these? if I asked you to evaluate similarity between these representative drawings, the characteristics that are related to the individual representatives, to the drawings, would be of greater importance than the properties of the concept of the lion. So these representatives are not very similar. It might even be possible that two representatives of the same concept are less similar than representatives of two different concepts. In other words, in a similarity estimation experiment, we might get a response that a lion is more similar to a rhino than to another lion. So we need to go back and analyze the concept of similarity in a more detailed manner. According to Goodman, similarity between two objects means nothing until it's completed by similarity with respect to property Z. In these figures, the property Z is that they all are lions. And according to being a lion, they are similar. But, as you say, they are not similar. So according to Goldstone, similarity between objects is seldom based on only one property Z. For example, the fact that they were lions. Instead, similarity estimation can change markedly depending on the properties that are implicated as relevant. For example, Barcelo showed that items that are seemingly quite different, namely children and jewelry, can be rated as highly similar if the property Z is things to retrieve from a burning house. So with the respect to property Z clause, Z might include many properties, and each property might be quite broad. And Goldstone added that there is a complex net of interactions between the attributes that are relevant with respect to property Z clause. For example, the other shared properties of the objects, and the expertise and background of the person who makes the comparison, who evaluates the items, and the context in which the comparison is made. We will come back to expertise later. So I noticed that my simple research project had become more and more messy. How to understand these competing factors of the set class properties and caudal characteristics. So more problem solving and persistence was needed with this. And then the good luck. I attended to a conference where one participant had run a multidimensional scaling analysis. So what was that? Already Shepard had demonstrated that similarity is inverse to distance. In other words, similarity is closeness in a space. And if we take the with respect to property Z clause, we can say that the number of dimensions on the geometric space represent the number of independent properties that are relevant for similarity comparisons. Additionally, since there are usually many properties, the solution is multidimensional. And the number of dimensions in the geometric space can be analyzed using multidimensional scaling. Multidimensional scaling is a procedure which uses the experimental distances between objects as its point of departure. The distances can be real, measured distances, or distances reflecting how closely two entities are related psychologically. So these psychological distances are, for example, similarity estimations. When this method is applied to data of distances, the objects are represented geometrically by points in multidimensional space, so that the interpoint distances correspond to the estimated experimental distances between these objects, and so that there is a minimum number of dimensions. To give you an idea of multidimensional scaling, let's take the lions again. So first we have a table of estimated distances between objects, in this case between lions. And here you see that the distance between one representative with itself is of course 0. They are at the same point. But then the distance between some other representatives is something else than 0. And these could be estimated distances, for example, from a similarity rating experiment. And then we analyze this kind of distance matrix data with multidimensional scaling, and we get a result where each lion has its coordinates on 1 or 2 or 3-dimensional space depending on the data. In this case, this is a 2-dimensional solution. And then it's up to the researcher to interpret the dimensions according to the properties of the objects on each dimension. In this case, I would perhaps say that dimension 1 could be explained by the color of the lion. You see these brown, yellow, then these very colorful things, and then black and white. Or it might have something to do as well with how much it looks like a lion. These two look more like a lion than these two cartoon-like figures. And then on dimension 2, it might have something to do with this. These have the head, and these have the whole body. And also that the head thing, the sitting lions and the standing lions. So these are interpretations of what we see from the dimensions. So this is to give you an idea of multidimensional scaling analysis. Well, I didn't study lions, unfortunately. So I studied similarity between set classes and representative chords, and I found, when I analyzed the data, that both set class properties and chordal characteristics were needed when I interpreted the dimensions. The set class properties were such as the dissonance or degree of dissonance, and it could be measured in terms of dissonance models presented in music psychological literature, or the number of sharp dissonances, IC class 1 instances in the set class. And the IC class 1 can be shown in a so-called interval class vector, and the first digit here shows the number of IC1 instances in the set class. This is an interval class vector for a pentachord, a pentad class chord with 5 or class with 5 pitch classes, and 4 IC1 instances is the maximum that can be found in a pentad class. Another set class property was the resemblance to the whole tone class. And whole tone class includes IC classes 2, 4, and 6. Whole tones, major triad, major thirds, and tritones. Again, it can be shown in a vector form, and for example, here you see another pentachord, interval class vector for another pentachord, and you can see that it has no other intervals or interval classes than instances of interval classes 2, 4, and 6. And this is actually the whole tone pentad class. Yet another factor was the inclusion relation. So some set classes have which I call familiar subset classes. And these familiar subset classes can be the major chord class or the minor chord class or the dominant 7th chord class. And these can be analyzed using so-called subset class vectors, but I will not go into details with them. And then sometimes the set class identity as such could be seen, like in this figure. You can see that the chords representing one set class locate on the same area. Of course, there are also chords that represent different set classes that are very close to each other. But the idea that these are on the same areas is somewhat surprising, especially with the participants of this study. They were non-musicians or musicians who knew nothing about pitch class set theory. They had never even heard about these things. And even non-musicians who had perhaps played some instrument for 5 years or less, but had no other formal musical training. Even with them, dimensions 3 and 4 in this analysis showed this kind of a pattern. So set classes have something that can be heard or in the representative chords. Then the chordal characteristics that were important in the similarity estimations were such as the evenness of the intervals. And evenness means the intervals between successive pitches, they were either relatively evenly distributed in the chord, like in the first 3 chords, or then there were both large and small intervals in the chords between the pitches, as you see in the 4th and 5th chord. Then another factor was the chord span, which means the interval between the lowest and the highest pitch. And again, here you can see chords with spans varying between 16 semitones and 22 semitones. And in some experiments, I had only 2 different chord spans, 15 and 16 semitones. And even that very small difference was very clear in the analysis. So listeners are very sensitive to these kind of small differences. Then the transposition of the chord was a factor, and the transposition was defined as the lowest pitch. And again, here you can see 4 different lowest pitches from G flat to A. And then in some chords, the successive pitches formed a traditional tonal chord. For example, here you can see minor triad, 3 lowest pitches, and major triad, the 3 highest pitches. And here is the major and minor triad. And so if it was between successive pitches, it was an important characteristic that explained similarity estimations. Sometimes the good advice is something that I could call weak signals. In my case, one professor mentioned semantic scales in a seminar, and I started to read about them. And then later another professor asked why not try them with these chords I was working with. And so I did. With semantic scales, the idea of similarity as a multidimensional concept is enhanced. The semantic scales give the participants some tools to show the dimensions or analyze the chords on different dimensions. In early studies using semantic scales, the number of scales was something like 40 or 50, which made all experiments very slow and exhaustive, because you had to analyze each object on 40 or 50 different scales. And if you had 10 objects, it would make 400 or 500 estimations, and if you had 20 or 100 objects, you can just make a calculation yourself. So I ended up to think about semantic scales that could be used to evaluate chords, and then I chose these 9 scales. And the data that is collected with semantic scales can be analyzed in at least 2 different ways. It's possible to evaluate each scale one at a time and analyze the connection between the chords and the scales. But it's also possible to form a distance matrix from these evaluations and then run a multidimensional scaling analysis of that data. And I've used both these methods, and they give relatively similar results. Of these 9 scales, these 4 correlated with each other, So smooth, calm, stable and round seem to indicate the same thing to the participants. And then rough, irritable, unstable and angular on the other end of the dimension. And these formed a dimension that I mentioned as consonance dissonance. And here you can see chords that were smooth, calm, stable and round on the left side. You can see that there are no sharp dissonances. They are pentatonic chords actually in different pitch orderings, but anyway it's the most consonant pentat class that exists. And then on the right side you see chords that are very dissonant, and you can see those sharp dissonances between the pitches, minor seconds, minor ninths, major sevenths and so on. These two, lush and colorful, barren, colorless, formed a lushness dimension. And lushness was connected with the dominant seventh chord, or resemblance with the dominant seventh chord. And again here you can see the lush chords, and you can see that there is the dominant seventh chord plus one extra pitch. And that's the same with the other chord. The C sharp does not belong to the dominant seventh. And then the colorless or barren chords, you see they are formed of piles of fourths. And that was the barren that I found in my studies. And then these two blurred, gloomy, clear light formed the third dimension, and the sparse dense was actually omitted because it didn't correlate with anything. And you can see that the blurred and gloomy chords were low. The lowest pitch is either B or B flat, while the clear and light chords, the lowest pitch is either C or D flat. Very small difference, but very clear effect. And also you see that the blurred and gloomy chords are the 15 semitone chords, and the light and clear chords are the 16 semitone chords. Very, very small difference, but very clear result. So this was the clarity dimension. So thus far I had studied set classes using chords as representatives. I had asked the participants to estimate similarity between two representatives or to evaluate the chords one by one on semantic scales. But the main problem was still there: how to study the concepts, not the representatives. And as I have stated, research is problem solving and it's good luck. And I had come into contact with Mari Tervaniemi and her brain laboratory. And I had learned about Oddball paradigm. And now the lion gives you the idea of the Oddball paradigm. A relatively rarely occurring deviant stimulus, which is the oddball, is presented among frequent standard stimuli. And the deviant elicites so-called event-related potentials, that is a response in the brain. Well, usually the task is not as easy as you can see there. The standard can also be a rule which is broken by the deviant. For example, in a pair of sounds, the first sound is always lower and the second is higher, and then the deviant is a pair of sounds where the higher sound comes first, and it breaks the rule. Or then all intervals in the standard are, for example, perfect fourths, and then the deviant is some other interval, for example, a major third. So I started to think about how I could use Oddball paradigm in experimental designs that I could run, because I had no access to the brain laboratory, where the paradigm is usually used. So my idea was that we can use abstract concepts as standards and as deviants, so that the items representing the standard concepts can differ. So this indicates that the concept is the rule. It was the property Z according to which the items were similar, like here. The concept is the lion, and then the deviant is the rhino. But all representatives of the concept are different. And this was my idea to start working with chords. And I started to use the paradigm in the following way. I chose 5 chords, and the participants played the sequence of 5 chords, and each sequence was repeated 3 times, successively. And 4 of the chords were the standards. They were identical in regard to the set class, and then the deviant, represented another set class. But all chords were different in chord span and transposition and pitch order and so on. And the participants' task was to listen to the sequence 3 times and then choose which is different. Intuitively, I didn't tell them anything about set classes or any other things. Just intuitively choose one. And because it was repeated 3 times, they had time to choose one and then count whether it was the first, second, third, fourth, or fifth. And that was the response. Give the number of the chord that was different. And I will play you one sequence of 5 chords now. You can hear it 3 times. And I ask you which one differs, and I also say, use your intuition. Don't analyze. Now let's see whether this works. Need to answer which was one the difference. I will tell you. It was the 3rd one, and it's more whole tone-like. It has no sharp dissonances as the other ones have. And as you see, the other ones are all different on pitch level, but they are similar on the set class level. So, in my opinion, this is a rather difficult task. I don't know what you said. Somebody said yes when I said it was a 3rd one. So somebody at least could hear it in this example. But the participants were better in this than I could ever imagine. And so with this kind of experimental design, it's possible to tell the participants that there are no correct or incorrect answers. Because the evaluation can be made according to the set class identity, which is, of course, was my interest in the work, but it's also possible to make it according to the chordal characteristics. And I also analyzed those chordal characteristics. For example, there was one chord had the lowest pitch and another chord had the highest pitch, and some chords had a familiar subchord between pitches. Some chords had even interval distribution and some other had uneven interval distribution. Sometimes there were small intervals, especially between the highest pitches, which also makes it sound very different. So I analyzed also these other chordal characteristics, but my main interest was in the set class. And in my opinion, thus far I have found no better way to analyze the set class identity factor with chords. So I promised to come back to the expertise of participants. It has been shown that trained participants respond using deep-level abstract cues or general principles, while non-trained or novice participants use surface-level cues and superficial features. This is true with, for example, physicists or chess players. But can we see that trained participants, meaning musically trained participants, use set class properties as cues, while less trained participants use chordal characteristics? So I was interested to see how formal musical training affects the way in which participants detect the set class in a complex experiment like that I showed you. And I chose 3 groups of participants. First group was formed of composers and theorists. They were either professionals or professional students. So they represented musicians with analysis-oriented practice. The second group included musicians with playing-oriented practice. They were professional instrumentalists or professional instrument students. And the third group was formed of participants with listening-oriented practice. This participant had not studied music, or they had perhaps played some instrument for a few years, but they were music listeners. And the oddball paradigm was used as described earlier, and in each test item there were 4 chords representing one set class and 1 representing the other set class. And the chordal characteristics on the surface level varied, as I have described earlier. And here you see main results from the first experiment. So as I said, even though the task was difficult, it was not impossible. And we can see that the participants with analysis-oriented practice, they really used the set classes as a cue, more often than surface-level cues. So the percentages are approximately 70-30. While with the listening-oriented participants, the percentages are the opposite. So it goes exactly as the earlier research says that it should go. And the playing-oriented participants were in the middle, 50-50 approximately. And I also analyzed some of those chordal characteristics, but I will not go into details today. Then I made another experiment comparing abstract and surface-level cues. And now I chose the same groups of participants, analysis orientation, playing orientation, and listening orientation, but so that they all had high scores in a musical ability test. And the possibility to find these kind of participants was yet another story of good luck. And yet another story of a conference. Now perhaps you understand that the conferences are the important part in the researcher's career. I had been in Bologna in a conference, and I had met Irma Järvelä. And Irma Järvelä is a gene study person, or they study biological basis of musical ability. And I later started to work with her group. And so in my own research, I was able to use the participants who had made these musical ability tests. And I could choose from that storage of more than 900 participants. I could choose those listening, analysis, and playing-oriented practice, those who had the high scores, maximum or maximum minus 1 point in the musical ability tests. So this indicates that according to musical ability tests, the participants were similar, but according to musical training, they were different. In this experiment, the abstract concept was not the set class. Instead, all chords in an item of 5 chords representing the same set class. And there were set classes from dyads, that is from intervals, to tetrachords, that is pitch classes, set classes with 4 pitch classes. Again, I take the lion to demonstrate this, what was done here. But now, I'm sorry, lion, we have to make an operation to split it into 3. And here you can see the parts of the lion on top of each other. And I will show you 5 sets of these parts of the lion, and I ask you which set differs from the others. You need some time to look at the figures. Which one is different? Yeah, it is the third one, because it is the only figure where the parts are on correct order from feet, nose, and or body, nose, and eyes. All the others are in incorrect order. And this was the idea of my experiment in music. And let's listen to two examples. The first one is very, very difficult. It was the most difficult example in this experiment, but I will play it anyway. Again, use your intuition and try to analyze, don't try to analyze, but try to listen which chord differs from the others. I will reveal the answer. According to the concept I was interested in, it is the second one. And what was the idea? Here you see these have the perfect fourth between the from the lowest pitch up, but this has not, it has the perfect fifth. And that was the very, very difficult idea that I was measuring. Is it possible to detect these kind of small differences in, for example, this kind of dissonant chord? And I will play you another one. It's more familiar chord, a tonal chord. Again, a tetrachord. And here you see the same pattern. In the deviant, sorry, it's very low. I don't know whether you can see. In the deviant, there was the perfect fifth from the lowest pitch, and in the standard chords, there was the perfect fourth. In other words, the deviant was the root position of the dominant seventh chord, and the standard was formed of the 3/4 inversions of the dominant seventh chord. And again, here you see the results. And before we go to the results, we can see the chance level. Because we had an experiment where you can, just by guessing, get 20%, one of the five. If you guess, you get 20% correct responses according to the intervallic ordering I was measuring here. So chance level is 20%. And here you can see a bigger difference between the analysis-oriented participants, which are here. They were able to do this task. They were able to detect the different intervallic ordering, even with the very, very dissonant tetrachords, the one I played you first. And you can also see that very nicely the figure, it goes down when there are more pitches and more dissonant chords, so it becomes more difficult. With playing-oriented participants and listening-oriented participants, we can't see any such pattern. And we can also see that it was a very difficult task on chance level, which means that it was guessing, or only a little above chance level. Again, this tells that this kind of different kind of orientation, which indicates that these are very, very well-trained people, these composers and theorists. They can do tasks and they can evaluate on deeper level characteristics than those who are less trained. Then the most recent project, I would say it's yet another good luck story, and it's yet another go to a conference story. I had given a lecture in a conference about music identification from melody, rhythm, and harmony. And I had written a proceedings article. And somebody had even read the article. So I received an email asking if I had ever continued the research. And the email came from Ivan, who was interested in the topic. And now we have a 3-year research project funded by Kone Foundation. And we study music identification from harmony. And we study aspects that are relevant in identification, such as the expertise of the participants and variation in the different kind of cues in the test items. And harmony is an abstract concept. I can use these labels, but you can't hear those labels. You hear only the representatives of those labels, and you can imagine, for example, these chord sequences, how they might sound. And each imagination might be different from the others. So I could start with the lion thing again, but I don't. Instead, I just give some examples about our research and what are the main problems there, or difficulties there. One is how to represent harmony without melodic cues. And why should we avoid melodic cues? Because we know that it's very easy for anybody to identify music from melody. Everybody can do that. And we are not interested in identification of music from melody, we are interested in identification from harmony. So we can also change the melodic cues so that we make incorrect melodic cues. But then we have also noticed that it makes the identification very difficult, because the listeners anyway listen to the melody cues and then they are incorrect and they start to think about something else and they don't focus on the harmony. So how to focus on the harmony? And I give some examples with incorrect melodic cues. And to avoid these incorrect melodic cues, we tried shepherd tones. Was thinking about any piece of music from that. And then we decided that we try to use a kind of reduction where the highest pitch somehow represents the melody, but not all details, sounding like. Now I saw that somebody already nodded, so it is easiest to recognize Elgar's combined circumstance from this last example. So, as I said, we also work on expertise and try to find out what kind of musical practice is relevant for music identification from harmony. And we work on familiarity with the pieces to be identified. And we are in half of our project and it doesn't seem to be very simple. So even though we have already solved some problems, we have faced a complex genre of new problems. And our research project is a process combining curiosity, persistence, and problem solving. So we need good luck, we need good advice. But I have to say, it's great.